This is the first part of our lecture, Introduction to Detection Probability. In this lecture, we'll learn about what is the probability of detecting the animals, how this probability depends on distance, and how we can estimate it. To this end, we'll look at the following topics. We'll learn how detection depends on distance between you and the animal. We'll learn how you can use the distances to estimate how detection probabilities decrease with increasing distance in a detection model, and we'll see what the parameters of the detection are that require estimation. We'll start with a simple theoretical example shown here on the image on the left. Suppose we have an array of 16 detectors, the black dots, arranged in a square configuration throughout our study area, each detector 500 meters apart. Suppose we also have 5 animals, the colored dots, randomly distributed, and we'll pretend for now that we know where each animal is. Each of these animals makes a number of calls, which are detected, or not, by the detectors. We assume our ability to detect a call decreases with increasing distance from the animal. For example, we can have a look at the red animal in the top left corner and indicate how easy it is to detect this animal with different shades of red. The darker shades of red indicate the areas close to the animal with high probability of detection. The lighter shades of red and yellows indicate the areas with lower or zero probability of detection. So when you're close to the animal, it's easy to detect it. When you get further away from the animal, it gets harder to detect it. You can do the same for each of the other animals. For example, the turquoise one or the green one. And we can think of these probabilities as a three-dimensional cone with highest probabilities right near the animal and decreasing the further you get away from the animal. As this cone is symmetrical in each direction, we'll collapse this cone into a one-dimensional detection function to make things easier. This simply shows how detection probabilities decrease with increasing distance. Zero distance is right at the animal. Each concentric ring in the left plot now corresponds to a slice under the detection function on the right. So this is your first look at a detection model. Detection model and detection function, the same thing, which is one of the things we need to estimate with an SCR model. This is what allows us to estimate how many of the animals we missed, or how many we did not detect. More specifically, we can look at the different distance bins and see how high the curve is in relation to 1. 1 indicates that we saw everything in this distance bin. The height of the curve tells us how many animals we detected of all the animals that were at this distance. For example, in the first distance bin, the curve is at about 0.9. So this is the first distance bin. And the curve comes up to about 0.9. This tells us that within the first 100 meters around us, between 0 and 100 meters, we detected about 90% of all the animals. In the next few slides, we're going to compare two scenarios. One, what we observe in the different distance bins when detection depends on distance, and scenario 2, what we would observe if animals made 10 calls and we would detect every call on each detector. Obviously, we'll detect more calls in scenario 2, shown on the right. But it turns out that a comparison of what we observe under these two scenarios allows us to estimate the detection model shown on the left. So we start with scenario 1 and continue with the example of 5 animals and the 16 detectors. We'll pretend we know where the animals are and can therefore measure the distance between the animals and the detectors. So for each time a call is detected on a detector, we can go ahead and measure the distance between the detector and the call. For example, the red animal makes a call and it is detected by detector 1. We can then measure the distance between the animal and the detector. Let's say each animal makes 10 calls. Remember, this is a theoretical example. And the number of calls detected depends on how far the detector is. For example, this red animal makes 10 calls, and 6 of these are detected on detector 1, 3 on detector 2, and none on the other detectors. So we go ahead and measure the distance from the detectors to the animal for each call detection. We can use these measured distances to start building the histogram, which will show us the distribution of all distances we observe. So the 6 calls detected at detector 1 fall into the second distance bin of the histogram, and the 3 calls detected at detector 2 fall into the third distance bin. We then look at the next animal, the green one, which was detected by 7 detectors at various distances. And we do the same thing as before and measure the distances between the animals and the detectors, between the animal and the detectors for each call that was detected, and add these distances to the histogram on the right. So we had 14 detections that fell within the second distance bin, 14 detections that fell within the third distance bin, and 1 detection that fell within the fourth distance bin. We do the same thing for the blue animal, which was detected by 7 detectors, for the turquoise, and the purple one. And we end up with a histogram of distances to each call that was detected. We also refer to this as the distribution of observed distances. Here, detection clearly depended on distance, and what we observe is a function of 2 things: how many detectors we have within a distance bin, and how high the detection probabilities are in that bin. What do I mean when I say how many detectors are in a distance bin? Let's have a look at an example. So if you look at the green animal, for example, and count the number of detectors that were within each distance bin, here shown as concentric circles around the green animal, we can see that there were no detectors in the first distance bin, so there couldn't have been any call detections of the green animals in this bin. There were 2 detectors within the second distance bin, 4 in the third, and so on. This is, of course, slightly different for each animal, but in principle, it's the same. Let's go back to our distribution of observed distances. We have relatively few detections in the first distance bin, but this is not surprising as there were not many detectors there. There were many more detections, 48, in the next distance bin, as there were many more detectors in this range, and the detection probabilities were still high. From then on, the number of detections in each distance bin decreased as the probabilities of detection dropped quickly at these distances. So here we looked at what we would observe when detection depends on distance. And now we'll have a look at what happens if each animal made 10 calls and all 10 calls were detected on each detector. This is our scenario 2. We'll build the equivalent distribution of distances, pretending we had detected all 10 calls, and we'll start with the red animal again and at the distances of all 10 calls to each detector to the histogram on the right. See, most of the distances are now in the higher distance bin, simply because there were more detectors at these higher ranges, and we didn't miss any calls just because they were too far away. So now what we observe is no longer a function of the detection probabilities, but only a function of how many detectors were within each bin. We do the same thing for the other 4 animals, and see that the pattern that emerges here is different from before, where detection depended on distance. Now the pattern is merely a function of how many detectors were within the individual bins. In the next step, we will compare the distribution we see here with the distribution of scenario 1. So let's have a look at the histogram on the right, and we'll turn this gray now, but the distribution is the same. And on the left, we have the histogram from scenario 1, and you can see that the y-axis are not on the same scale. One goes up to 50 and the other goes up to 140. So to start our comparison, we'll bring the left one onto the same scale on the right, simply by squashing it down and turning it black. And then we can add the histogram, the black histogram, to the gray one. And we can tell two things from this comparison already. One, we only detected a small fraction of all call detector combinations. The black distribution is much smaller than the gray. And secondly, those calls that we did detect were detected by detectors at close ranges. We'll now have a look at what proportion of calls we did detect out of all calls that we could have detected. How does the black bar compare to the gray bar in each distance bin? We'll do this by converting the black and gray histogram on the right into a proportion plot on the left. Here in the left plot, the gray bars from the right represent 100%. And so if we had detected all possible calls in each bin, then this is how many we would have detected. So then the proportion would equal 1. The black bar, on the other hand, represents what we actually did observe. So the black bar on the left gives you the proportion we did detect of all the calls that we could have detected. For example, in the first bin, we could have detected 20 calls, but we only detected 18. And so the proportion we draw in black on the left side is 0.9. In the second bin, we could have observed 80 calls, but we only detected 48 calls. So the proportion we draw in for the second bar on the left is 0.6. And we do this for the remaining distance bins, which were all 0 past 1,000 meters, as no detections were made out there. So once we've done this, a shape emerges. Recognize this shape? Yes, this is very much like the detection function we spoke about at the beginning. This detection function is generally defined by two parameters. One is referred to as G0 and the other as sigma. G0 tells us what the detection probabilities are at 0 distance. Can we detect all calls when we are right next to the animal? And sigma tells us how quickly the detection probabilities decrease with increasing distance from the animal. The larger the values for sigma, the slower the decrease in detection probabilities. So we can draw in the same line or the equivalent line and the parameters on the proportion plot on the left. So far we've pretended that we know how many calls each animal made, which was 10 in this example. In reality, we do not know this, of course. So using distance alone, we would not be able to get the proportions as shown on the left side here on this slide. And therefore, we would not be able to estimate the parameters G0 and sigma. In the next lecture, part 2 of this chapter, chapter 1, we'll learn how we can use the ideas from mark recapture or capture recapture to help us with estimating these parameters while getting around the problem of not knowing how many calls each animal made. In the lecture Introduction to SCR, we'll then learn how we can get around not knowing the distances. Here are some key points to take away from this lecture. Detection generally depends on the distance between the detector and the animals that make the calls. The further an animal is, the less likely it is that it is detected. Detection probabilities can be estimated using the distances to the detections. And we'll learn later on how SCR can do this even without knowing the distances.